Hello, folks. Nice to see you here. Good morning. I wanted to start with a joke, so my talk today will be like a morning coffee from a vending machine. You don't know what to expect, yes, but it can be surprisingly good. Especially because there is like only 200 slides, so it will be like a warming drink at the beginning. So my name is Maksim Nabokikh. I'm a principal engineer in Palark, and in my free time I contribute a lot to open source projects, like basically some authentication features to Kubernetes, a lot of features to DEX, and little things to other projects. Yeah, I like to contribute. So my today's talk will be about encryption, data in etcd, and why KMS with matters. So a couple of words about our company. So we are Palark, we are DevOps experts, we are a service company. So if you have DevOps related problem, we can consult you, or if you don't have engineers to solve your DevOps related things, so we can provide you a team of engineers. That's who we are. Okay, intro and motivation. And I will not tell you the motivation for this talk just right now, because this is the cherry on pie, so this is the most interesting part of the talk. So now let's keep this a secret. What I can tell you is that I had some R&D tasks connected to etcd and how data flows in it at rest, and I started researching how it works. And I just want all of you to walk the same path I walked through till the very end. So please stay with me for till the end of the talk. So the plan for today's talk is, first of all, we will discuss how data actually lands in etcd. Then we will speak about why just storing data is not enough. And the final part will be my secret task and how I solved it. Yeah, so how data flows into etcd. The problem is etcd is just a key value storage. It's not simple, but it's key value. So in terms of storing data, it's simple. But Kubernetes itself is a complicated object system. So there are API versions, object schemas, versionings, defaultings, many things. So etcd can efficiently store bytes, but Kubernetes does the rest in terms of how we actually store the data. Kubernetes and etcd, they're perfect together. They're like the best duo, like SpongeBob and Patrick. Yes, like Rick and Morty, like Shrek and Donkey. Yeah, they're perfect. But Kubernetes does a lot of work always, and etcd stores the data. How data actually flows into etcd. So at first, user submits a resource, for example, a secret. Yeah, submits a secret to Kubernetes. So from client, data flows to Kubernetes API server. API server is a complicated thing. So inside the API server, there are many different layers inside, like in the code of Kube API server. There is a router that routes requests, REST layer, storage layer, and from the router, raw data flows to REST layer, then Go objects flows to the storage layer, and finally we persist this encoded data into etcd. So etcd is a final persistent storage. Now we will focus specifically on the Kube API server storage layer, on the API server part. Inside the API server, we have a storage interface to work with different storages. It's stored in the API server package. And this is an abstraction for different backends, but we only know etcd, but there may be, other backends. And responsible of this interface is just like create, update, delete, list, get objects from etcd or from other storages. Yeah, interface looks like this, pretty simple, nothing complicated. Then there is an implementation of this interface inside Kube API server, the etcd3 storage. It's also located in the API server package, and it implements the storage interface. It contains etcd client to work with etcd. And this implementation can encode, decode, and transform the data while writing and reading data from etcd. So how it works, the flow chart. We have Kubernetes object. First of all, we encode it into something. Then it goes through the value transformer chain, and we write it to etcd. This is the write path. Then, if we want to read it from etcd, the data goes through value transformer chain in reversed order. Then we decode this data, and then now we have a Kubernetes object. This is the read path. We will today talk a lot about write path and read path. Okay, so on the right you can see the flowchart. Now let's focus on specific things of this flow. The first thing will be value transformer chain, and this is also an interface inside API server. Wow. This is the core interface for transforming values before storage and from the storage. And the interface looks like this. So basically, there are only two methods. First method is when we are reading something from storage. It's called transform from storage. And the second one is when we are storing data into storage. It's called transform to storage. And these transformers, they can be combined together into transformer chain. And all transformers can be configured via config file. We will discuss this config a little bit later in the talk. So yes. Then we are this is the serialization layer. It starts in another thing, in another place in the API machinery package. Encoding and decoding we're doing with the codec. And codec is in charge of converting Go structures, Go types into bytes. Embedded types we convert to protobuf. If this is a custom resource you added to your KubeAPI server with CRD, it will be converted to JSON. And it also handles versioning, defaulting, and other things in KubeAPI. Okay, so conclusion for this part. So Kubernetes stores only safe, versioned, validated bytes into etcd. Storage layer is well abstracted. There are a lot of interfaces that you can re-implement. And there is a space for customization and embedding into API server because it's well abstracted. Okay, so first part we covered, then go to the second part and talk why just storing data is not enough. Okay, why it is not enough? So etcd stores everything like secrets, tokens, credentials, and also workloads like pods, deployments, stateful sets, different things. Yeah, and the problem is when we, in a shared environment or in a cloud environment, when we make etcd volume snapshot, it can leak sensitive data because it's not encoded anyhow into etcd. Okay, so in Kubernetes 1.7, so this version introduced encryption providers. What is it? This is a pluggable mechanism with different encryption strategies. All the strategies declared in the encryption configuration, and supported providers are, so there are a lot of supported providers. You can read about them in the doc, but and the identity is not even a provider. This is just a helper. But the last one, KMS, this is the most interesting one to talk about. So we will focus on this specific provider. Why KMS was invented in the first place? So the problem is key management in Kubernetes was do-it-yourself for all other encryption providers. What does it mean? So if you want to rotate keys for encryption, you need to do it manually. There is no help in there for you. And keys for all other encryption methods besides KMS, they are stored on disk, on the control plane node with the same Kubernetes. So it's not secure. So the solution was to upload key operations to external key management system, or as we know, KMS. There are different KMS like AWS, GCP, Azure has its own KMS also, and HashiCorp Vault, we also can say that this is the key management system. How we can configure KMS provider in Kubernetes? So there is a specific flag for the KubeAPI server that points to a configuration file, and there is a format of configuration file. The encryption configuration I've told you before about, this is it. There you can see resources that will be encrypted at rest. In my example, there are secrets and config maps. And the second part is we see settings for encryption providers. There may be more than one, but on my screen, this is just one configured provider. And we specify name, timeout, and endpoint for the Unix socket. Why the Unix socket? Why do we need the Unix socket? Because there is this thing called KMS plugin. What KMS plugin does? So this KMS plugin is basically a gRPC server. It implements predefined protobuf interface. There are methods, only 2 methods in this interface. The first one is encrypt, and the second one is decrypt. And this gRPC server listens on the Unix socket and exposes these 2 methods. The duty of the KMS plugin is to forward cryptographic operations to an external KMS. So we need a plugin to talk with Kubernetes as a proxy or like this. So how KMS plugin works? There is a simple flow chart. So we have API server, KMS plugin, and external KMS. These 2 communicate via Unix socket, and these 2 communicate with API. The detailed flow of KMS and how it encrypts data is just a little bit complicated. Let's discuss it because this is important. Okay, at first, client sends request to KubeAPI server to create something, an object. Then KubeAPI server generates DEC. DEC is a data encryption key. So this is the key Kubernetes will use to encrypt the data, or to encrypt this particular object. Then with this DEC we are going to KMS plugin. KMS plugin goes with this DEC to external KMS, and KMS encrypts the DEC with the KEC. KEC we know this is the same as LOL. You know this, okay? But this is of course a joke. KEC is a key encryption key. It never leaves KMS, and we use this only to encrypt data encryption keys. I know this can be tough to understand, so let's try more simple example. You have data, like a file, like I don't know, paper with some data. You store this data in some safe. You probably bought this on a flea market, so something not that secure, yeah. There you store your file. Then the key for this this small safe you store in the big protected vault. And this is like really protected vault with some fancy things like probably biometric checks, or so you don't need to care about the security of this vault. This is pretty secure, and basically, yeah. So this is how the encryption in KMS in Kubernetes works. Yeah. So then encrypted DEC returned to the KubeAPI server. KubeAPI server encrypts the data using the DEC, and then both encrypted DEC and encrypted data stored together in etcd. This is it. This is how it works. There are some shortcomings. Like for example, in this implementation, there is no caching, so every API request results in gRPC call to a plugin. And as a conclusion, we are going to KMS every time, and we are spending money because in the cloud you're paying for KMS requests. So no observability, no metrics, no status checks, nothing for the plugin. So the plugin itself was a performance bottleneck because you need to call it every time, and if it fails, your entire cluster also can fail on read-write requests. The interface was limited, only 2 methods like encrypt and decrypt, so it's impossible to rotate keys inside KMS because plugin cannot do anything smart there. Okay, so clients need to pay a lot to make their clusters unstable. As we see, nobody wants to use this encryption at all because there are a lot of disadvantages in this. And that's why KMS v2 was invented, and this is the real deal. The goals of KMS v2 were like reduce KMS API calls to lower latency and costs, add some key metadata, so which key was used to encrypt DEC, at what time, by which plugin, so metadata. We also wanted to support key rotation because without rotation it's just pointless to use KMS. we also wanted to use some envelope format that can be controlled by a plugin, allow plugin side caching, and add some space for extensibility. Yeah, and there is a new flow. So for KMS v2, the second version of KMS implementation in Kubernetes, there is a new flow, and it starts with Kubernetes API server that generate the DEC seed, not the DEC, but the DEC seed. What is the DEC seed? This is the specific seed, and this seed is used to generate DECs in Kube API server. Okay, so then API server goes to KMS plugin to encrypt this seed, not the key, but the seed. The seed is encrypted using KEK, then returned, and now Kube API server has the encrypted seed. And Kubernetes API server does it not for every request, but only on startup or on key rotation. Yeah, so when API server doesn't have the key in cache, so it does it, not for every object. Yeah, and then API server generates the DEC from the DEC seed, and besides the seed, we use like the pass and CD to the object. So we can generate the same DEC if we have the seed, but it's unique for an object. Then DEC is used to encrypt the secret, and then into etcd we store both like encrypted DEC seed, encrypted secret, and some metadata, which key was used to encrypt the DEC seed at the first place. Okay, what actually goes into etcd? So the format of etcd data looks like this now. So it's JSON with fields. This one is encrypted DEC seed. There is a key UID. And you can also see encrypted data, and there are annotations, which plugin was used, when it was encrypted, and so on. Okay, what is this performance in V2? So in V1, we spent 25 milliseconds on writing, and in the second version only 7 milliseconds, so it's like 4 times better. Yeah, read like the same values. And initial list of secrets in KMS V1, it was like 5 minutes. But with the second version now, it's only 100 milliseconds. So this is the win. Yeah. Key rotation is also possible in KMS v2 because there is, besides decrypt and encrypt, there is additional method called status. So now the interface for KMS plugins has 3 methods. And the status methods can return which key ID is used now for encryption. Kube API server can check this endpoint, and if its key, when key is substituted, Kubernetes API server can also re-encrypt the data because we can understand that key was rotated in KMS. Okay, so rotation trigger was manual, now it's plugin defined. Re-encryption, Kubernetes API server must do it in first version, and in second version, plugin can defer or even avoid re-encryption. Because we have metadata which key we use, so we can send the metadata to KMS, and it can decrypt the data using the specific key. So now there is also key metadata, and downtime risks, they were higher because when KMS V1 plugin didn't work, we failed all the write-read operations, but now, because everything is cached, we are not failing these operations. This is better. Okay, why it matters: low costs, low latency, real key management, plugin freedom, and better user adaptation. So now users finally can use the feature. Okay, I covered the encryption part in Kubernetes, so I just turned data is not enough. And then the final, the part I hope you all were waiting. My secret task and how I solved it. And my secret task was to make etcd more secure. Even more secure, even like to go beyond encryption. So the problem is that if you have etcd access, you have cluster gold mode, right? If attackers or misconfigured systems, so they can modify secrets, they can inject configuration, they can mask malicious workloads. For example, you can run a miner in a cluster if you have etcd access. And these operations, we will not see these operations with etcd in Kubernetes audit log because they are going around API server. Yeah, so you cannot detect them. And what I think that tampering detection is critical, not just data secrecy. Yeah, so we need to detect if a user has some access to etcd. So can we prove what's stored in etcd was written by a trusted system and has not been altered by anybody else? So this is the question. So encryption is not sufficient there because encryption. So I missed the slide. Sorry. So our solution is digital signatures. To add digital signatures to Kubernetes, not just encryption, but also signed data. Why encryption is not enough? So encryption can prevent leakage of the data, as we discussed previously, but detect tampering with encryption is not, I would say, possible. And also, so that data with encryption is not recoverable. So you cannot recover the data if you lose keys for encryption. Okay, so why KMS v2 plugins are not enough there to solve our task with digital signatures? KMS plugins do not work with payload. Yeah, as we've seen before, they only work with DEX, but we want to sign the actual payload, not the DEX. And in KMS v2 plugins, it's pointless because we are working only with DEX seeds, which is not the DEX even. Okay, so there is no way to sign data, store signatures, verify integrity, nothing like this. So we cannot tell the data was changed after encryption, and I would say encryption with calls to gRPC plugins, it can be heavy to apply to all resources in Kubernetes. So in plugin socket, they has also be protected. What I'm going to tell next is maybe weird, but we decided to add a patch for the KubeAPI server to add digital signatures just as a proof of concept. So our sign-in transformer chain now looks like this. So user object, we encode it, then we signed it, then encrypt it, and then store it in etcd. There is our interface. We reused the transformer interface I've shown you before. This is our sign-in transformer. It has public keys for validating signatures and a signer to sign the data. And for sign-in, we use JOSE. JOSE, what is JOSE? JOSE is a JSON object sign-in and encryption format. And it's well-defined standard. It's compatible with different keys. And it can also use the ECDCA. And this is widely supported algorithm. So we were happy to use this one. This library. So our write path looks simple. So there is only one method, like the signer signs the data, and then we serialize the data and store it in etcd. The format for the data is, so we use flattened the GVS JSON serialization syntax. It looks like this. So payload is the actual Kubernetes object. Protected and header, so these two fields are the metadata of which key was used to sign the data. And signature is the main part why we are doing this. Yeah, the signature for the payload. So it was the write path. The read path is a little bit more complicated. So transform from storage method looked like this. So we, first of all, we are parsing the signature from the etcd object. If there is no signature, we need to react somehow. Yes. Then we verify signature with the public keys. If the signature is not valid, we need to also react somehow to this. And then finally, we return the payload. So the read path looks like this. So if the signature is valid, we decode the object. If the object is invalid, so we reject it because there were some malicious actions done with etcd. But it can be, maybe this is not what we wanted, right? Because if we reject the request, we can fail a lot of controllers from working just because we are rejecting a lot of list requests or GET requests, so we can break the Kubernetes like this. But we wanted just to detect the tampering, not to break the Kubernetes, so we decided to go with another thing. So in terms of valid pass, this is the same, but for invalid pass, we, instead of throwing an error, we still decode this object, but in addition, we add the annotation to audit log that this object was was with a missing signature or was with invalid signature. Yeah, and we also increase the counter, the metric, to be able to alert if something happened with that CD data. What we gain, so trusted write path, tamper detection, auditable writes, key rotation possible because for keys we use not a single public key but the public key set, so we can rotate keys now. And it's still compatible with encryption layer, so we, after signing the data, we can still encrypt the data. And these two layers, they're compatible because they are the parts of the transformer chain. What this could like in upstream Kubernetes, because I believe Kubernetes clusters can benefit from this feature, but how can we add it to upstream? I wrote the detailed plan here, but then I deleted this. We have already submitted KEPs before, so maybe this will be a new one. I don't know. We will see. Okay, this is pretty much it. Let's dive into conclusion and the future of this, of what I've been talking about today. So, encryption works well in Kubernetes. Now with KMS v2, it really worth enabling or trying, so you can try it yourself. KMS v2 fixed many things, not all, but a lot of things. So now it's usable. Encryption is not good for tampering detection. Digital signatures at rest, as I believe, this is a missing primitive. Patching kube-API server is the only option now if you want to do something at rest with Kubernetes data. So this is the only option. You can't do anything besides it if you want. And digital signatures might be the next step for regulated or security-sensitive clusters. This is maybe a little bit exaggerated, but we need something at the end of the talk like this. Thank you so much.
Thank you very much. It's time for Q&A now. Any questions? I see the hand raised.
Do I need the mic or?
Yeah, you need the mic. Yeah. It's over there. Your left.
Thanks for the talk. Yeah, really deep technical back. I have a question. Like, how do you manage their storage for their digital signature certificate private key? So it's like chicken and egg?
For now, I'm telling you the truth. We are still testing this feature. Right now, we just embed this into kube-API server binary in many places. But we are still thinking about how we want to do this. Do we want to reuse KMS, for example? Like maybe we want to send data with KMS. We will see. I don't have the real answer right now because we need to test this a little bit more. So that's why I didn't cover it in the talk.
Well, I guess thank you for telling us the truth.
Yeah, but I'm a honest man.
Thank you for the talk. I have a short question. So at the last stage, you were showing us that you've chosen to just basically log the incorrectly signed request rather than actually reject them. Did you come across any false positives during this testing stage?
I would say for now we are still testing this. We are not consider this feature as fully production ready. So we are looking through alerts, through metrics, through audit logs. Sometimes, when the data is not, prepared, you have Kubernetes clusters where this feature was not enabled in the first place. then we enable the features, and then we'll like see a lot of alerts because there are a lot of unsigned objects inside the etcd. But after this, I believe it works well. So because when you are touching the object through Kubernetes, at rest it became signed, and then everything works well for now. Yeah, this is it.
Any other questions? Actually, I have one.
Perfect.
So you told us that you have submitted the key basically.
No. I'm just planning or considering
Right,
this.
right. But you did that before.
Before, yes, of course.
Right. So I just wanted to, and I understand that it might be subject to a different talk, but maybe in brief you could sum up your experience with submitting patches to Kubernetes. How long does it typically take for upstream to accept it?
If the patch is pretty simple, it takes just, I would say, 3 releases of Kubernetes to make it generally available. So it's like a year of work. And after this, you need 2 releases to delete alpha and beta feature gateways from the code. So it takes like a year and a half to fully provide the feature. Also, you need some time to discuss the KEP with the team. Probably also like 1 or 2 months for this. Yeah, if the feature is simple. If the feature is not simple, it may take years.
So it's like it took with KMS, if I read it right, with KMS version 2, it was from Kubernetes version 7, 1.7 to 1.29.
Yes. Now.
That's around 7 years or something.
Yeah, kind of, yes. But my favorite KEP is about, I added a small function, maybe you've heard about this. With kubectl now you can type like who am I command, and now you can get who you are, like your name, your groups, your extra attributes. This is the feature, a small feature for debugging. And this feature needed like the kubectl command. This is one team, the API for authentication. This is another team. And you need to talk with them, negotiate everything, and then promote the feature. So even this small thing took like a lot. But that's why we love Kubernetes. It's pretty stable, and it almost never breaks promises.
And you
As
your life for years.
yeah. Yes.
Any other questions here? Oh, maybe some of you will have some questions later. In which case, the speaker will wait for you in hall 3 for some duration. So please don't postpone it. On the final slide here, you see the QR code. Please follow the link to rate the talk and leave your feedback. Really important for us, the programming committee, and the speaker. You can log in using the code on your page. If you face any difficulties with logging in, please approach our help team, the people who look like this one. And so after the presentation, the coffee break will be served in the foyer, hall 3 and hall something like that. So applause to the speaker. Thank you.